whatever meters.
Okay, so the last speaker is Santosh from Vempala, and he'll tell us his title.
Yeah. K or outside K.
So you didn't use the LLM to write your talk?
So you?
You didn't use the LLM to write your talk?
No, yeah. See if you can get your see if you can get your AI to do this. Okay. Here's my chance to say a little bit about Avrim. Avrim was my advisor. He taught me the perceptron algorithm, pack learning, SQ algorithms, Chernoff bounds. I can go on. But he also showed me through live daily example the qualities of a researcher that I strive to emulate, largely unsuccessfully, but I'm still trying. The value and joy of simplicity and clarity, okay? And generosity and kindness to everyone that you run into. And then working hard and being happy while you're working hard. So it was great, and so thank you. Yeah. This problem that I'm going to talk about is the problem that he told me he may not remember. The very first day I walked into his office, basically, it was in Wien Hall, the 4th floor. This green chalkboards, and he started drawing on the board, and he said, "Oh, I've got some red points, okay, and some blue points, and the red can be separated from the blue by some hyperplanes." Okay, so that's what you know about the red and the blue points, and now your goal is to learn some rule that separates the red from the blue. Given a new point, tell me if it's red or blue. Okay, so as I learned shortly after, these are drawn from a distribution, they're drawn independently, and there's a labeling function. So the function is, in this case, f of x. So everything is in n-dimensional space. F of x is 1 if all the points lie on the same side of, or the positive side of a set of hyperplanes. So this is maybe W1, and then this is W2, and so on. And so it's 1 if they're all, if x has a positive inner product with all of them, and otherwise it's -1. That's your labeling function. You don't know the w's, of course. That's the point. You don't know the thing. And you could, in general, have different thresholds here, theta I.
But you know the number of hyperplanes.
Yes. So you have I going from 1 to k, let's say. Okay. Good. Now, this problem generalizes DNF, which was a nice problem in the original pack learning paper, because in DNF you want to do x1 and x2 and x3 bar. No, that's not DNF. Somebody should have been. Yeah, and so on, right? Okay, and so each of these is a hyperplane, and you want. So now, so the simplest case would be I have 2 planes. Let me think of each plane as a little threshold function of the same inputs, and then there's one node here, which is the AND. So it should be on the positive side of this and the positive side of this. This is W1, this is W2. And so you would call this a 2-layer neural network with 3 nodes. And so there's this classic result of Blum and Rivest, originally 88, but I think the journal version is a little later, 92, which says that training a 3-node neural network is NP complete, is NP hard. Okay. Training a 3-node neural network is NP hard. Okay. Good. So even though you know there are 2 planes, you can't find them. Even more so, if you have k, an intersection of k hyperplanes, learning k half space intersection using k times n to the 1 minus epsilon planes or half spaces is also hard. Okay? So you need, even if you use more planes, because that's the thing about learning, right? You don't have to learn exactly that. You could come up with a whole bunch of them as long as there's enough data supporting that those do a valid classification, you're in great shape. But even if you use this many more, you're not going to work. It's not going to work. So I guess he was setting me up, but we continued anyway. And now the problem is nice because the VC dimension itself is small, right? So the VC dimension of this problem, which tells you how many samples you'll need from an arbitrary distribution, is only scales as the dimension times the number of planes. Because the VC dimension of a single hyperplane, single half space is linear in the dimension times k. So in principle, to learn any distribution, or to learn over any distribution to accuracy epsilon, you only need nk over epsilon times log factors, samples. So it's not the sample complexity, it's really hitting a computational difficulty. Okay, so as a first step, let's, I think below this, maybe it's hard to read. It's useful to, let's think of, in this problem, there is a margin. So not only do we have these planes, but there's a little region around these where there are no points. Okay? So we'll call this a margin, and we'll use that quite extensively. So one notion of margin is robustness. So we'll say a concept classes are robust. And this just means that rho, if I take over the distribution D, any pair of points x, y, where the function, they have different labels. So the label has changed. The distance must be at least something. So 2 points with different labels must be at least at some distance apart. So then the minimum of this x minus y, let's say Euclidean distance, and this is what we're calling rho. Okay, so 2 points with different labels, so a plus and a minus point must be a distance at least rho. So that really looks like, if I have these as my concept classes, then if I take any point and put a ball around it of radius rho, I don't hit a negative. So basically, I have this region with no negatives. This is positive, that has no negatives. Okay, great. And then there's a few results. So I ended up talking about this problem with a young woman from Harvard at the time, and we wrote a paper back in '99, which showed that you can solve this problem for a robust distribution with complexity k to the order of k over rho squared. Okay? So if you have constant margin and a constant number of planes, you can do this. It still makes sense because even if k is, right? So for a constant number of planes, you get something with margin. Later that year, I ended up marrying her. So, but then this was improved by Clivens and Servideo in 2008 to the minimum of k over rho to the k log 1 over rho, yes, and log k over rho to the order of square root 1 over rho log k. Okay, significantly better. And then later, Gottlieb, Kontrowicz, and Sivan to k to the 1 over rho square. So that's the status. Okay? So for constant margin, it scales, you get a polynomial in the number of planes. They're all based on random projection, all random projection. Yeah, which was the original technique.
Guys are different, or just a different analysis?
Different analysis, also different tools, significant tools, yeah. Okay, now notice here though that when we're talking about so the title of this talk is learning polyhedra with margins, with a margin. Okay. Say again? Right, so the definition of rho here, I avoided it here. This is with all points lying 1. Otherwise, there would be whatever is the maximum distance scaling here. Good. Great. Now, if you take a polytope, like we talk a polytope that's full dimensional, we already know that k is at least n plus 1. You need at least a simplex. And if you take a distribution, even a mild distribution like a Gaussian, or if you consider hyperplanes over the Boolean cube, then you end up with rho being smaller than 1 over poly n. So this is a typical setting that will show up. You have at least dimension number of planes, and your margin is 1 over poly n. In these cases, these lower bound, these algorithms are all 2 to the omega n, or worse. They're exponential time algorithms. Right, so we don't know how to learn a polytope over a Gaussian distribution better than exponential time. Okay, so then just this year, result by Ullman, Patel, and Servideo for just 2 planes, k equal to 2, so the original problem, showed, give an algorithm that can learn from any distribution, and they don't even need a margin, and its complexity is 2 to the square root n, 2 to the O tilde square root n. Okay, so there are some log factors, but it's not 2 to the n, it's 2 to the square root n. Okay, and for general k, it is 2 to the root n times log n to the k. So it's doubly exponential in k, but for any fixed k, it's O tilde root n in the exponent. Great. Okay. Now, these bounds here, the 2 to the square root n, 2 to the omega n, they're here for a reason, and there are at least 2 reasons that suggest that there are inherent lower bounds here. There's an inherent difficulty here. So one of them comes from statistical query methods, statistical query algorithms. I won't go into defining those, but you can think of them as all but Gaussian elimination. Okay, so you can phrase algorithms, known algorithms for this problem in that setting. There are, of course, other exceptions. That's a simplification, but statistical query algorithms capture a vast majority of known algorithms. And there's a result by Clivans and Scherstov from 07. Now it says that for k equal to root n planes, any statistical query algorithm and rho 1 over poly n, any statistical query algorithm has complexity 2 to the omega root n. Okay, so it doesn't matter. So this is the lower bound. If you have an intersection of root n planes and your margin is 1 over poly n, you're going to hit this root n 2 to the omega root n. Then there's also cryptographic lower bounds based on the hardness of well-known lattice problems, in particular the problem of unique shortest vector. And assuming that the unique vector is unique up to a factor of dimension to the 1.5, n to the 1.5, we get again a lower bound of 2 to the omega root n. And this is basically work of Teagle from 24. Okay, so both from an SQ point of view and assuming lattice hardness, and this is unique SVP, shortest vector problem, up to n to the 1.5. We don't know how to do it up to any poly n factor. So it's a reasonable assumption at the moment. We have these lower bounds. So that's the status. And so the result I want to talk about today is this work with Patel, Shamal Patel. And here is the theorem. There exists an algorithm to learn an intersection to epsilon delta pack learn, the usual definition, an intersection of k half spaces over any distribution D that has margin rho. Okay, so that's the full specification. So k half spaces, and you have margin rho. In time 2 to the order of square root n log 1 over rho and log k. Okay. So yeah, so you can learn any distribution to correctly classify 1 minus epsilon distribution, and the algorithm works with probability 1 minus delta. Now notice that if you consider k equals poly n, and rho is say at least 1 over some poly n, then this is 2 to the root n. Okay, and that means it's almost tight, but at least for SQ algorithms and crypto, with respect to crypto law. Without either you'd have to break a crypto lower bound or give a non-SQ algorithm. There is a corollary which follows almost immediately for the Boolean cube, which is that if you consider an intersection of k half spaces of with integer weights, magnitude at most w. So the weights each have, the coefficients in the integer vector have weights at most w. Then you don't need to worry about, there's no margin. You don't need to say margin anymore, because assuming this over the Boolean cube, plus minus 1 to the n, automatically gives you a margin that's polynomial in NW, can be learned, epsilon delta pack learned in time 2 to the order of square root n. Now here we get log NW log k. Okay. And this is simply because over the Boolean cube, low weight half spaces have 1 over poly n margin, 1 over poly n W margin. And this is also tight. There's lower bounds showing that this has a SQ lower bound as well. One last corollary I'll mention is that these are hard margins so far I've described. That means there is absolutely no point allowed in this margin. And that's not the case for, let's say, the Gaussian distribution, or a mixture of Gaussians, or a log concave distribution. And so we have a second version of the theorem for soft margins. And so all I'm going to do here is tell you what a soft margin is, which just means that, so D has a soft margin rho, means that with probability 1 minus eta, the margin is rho. That, I just mean that for 1 minus eta of D, so most points, or some 1 minus eta fraction of points, are at distance rho. You're allowed to have eta points here, and then the 1 minus eta must be away. At most, eta points are allowed in the margin. And so whatever this eta is, the theorem says you can learn 1 minus eta minus epsilon of D in the same time complexity, same complexity. Now the nice thing is that for Gaussians, log concave, and all these distributions, and in fact the ones that are used in the lower bounds, once you set eta to be 1 over poly n, rho is already at least 1 over poly n. So eta 1 over poly n implies rho is 1 over poly n. Right? If you take a Gaussian distribution and ask how much is in any small band, if the fraction drops at least linearly in the band. So you can apply for these distributions as well. Okay, so that's the full thing. Now, so this sounds nice there, but here's the main reason why I'm giving this talk, which is that the algorithm and proof I can do on this board. Okay, so a couple of preliminaries, just to, we can assume without loss of generality that, I will have to erase, yeah, I got it. Thank you. That the half spaces all pass through the origin. So we can assume that theta i's are all 0, and that the norms are all equal to 1 without loss of generality by adding 2 more dimensions. We're going to add 2 more dimensions without, and the margin will change only by a constant factor. So it's a fairly standard trick, just to be a little bit careful, but it is so you can assume this, and so I'm going to assume this further. Okay. So we have planes going through the origin, and the points are all unit vectors. The other fact is the following. There are, as you might notice, 2 types of margins. One is this rho robust margin that I just defined over there, the minimum distance between a positive point and a negative point. Another notion of margin is you say it's a rho margin. Let's call this margin, and that's rho robust. Means that for any x for which f of x is negative, it's a negative point, there exists some I such that wi dot x minus theta I is less than minus rho. Right? So what this is saying is that if I tell you this point is negative, there is at least one plane that so that it's a distance rho from that plane. This is a little bit different from this notion of margin, right? Because here, this is rho robust. Rho margin would be this. You have to be this point, for example, is not a distance from either of them. So this is rho margin, that's rho robust. There is some plane that you're far from, and this one is you're just far from. So this is obviously a stronger notion. You're asking for more. But the fact is that rho robust implies rho squared margin. So for the purposes of our algorithms and bounds, we can assume the stronger one. Okay, that's okay. Great. With that in mind, now with that all said, here is the algorithm. So algorithm 1. So we have some distribution D, right? And we have the function f that labels. Sample a set P of positive examples. Positives are supposed to be red, so let me stick to that. And then sample n of negative examples. Okay? And then let me set up this set, which is H equals the set of vectors in the unit ball which correctly classify this sample. So w dot x is greater than 0 for x in P, and w dot x is less than 0 for x in N. Okay? Just half spaces that correctly classify the sample. And then step 4 is sample w uniformly from the set H. Uniformly. Just a uniform vector that satisfies this, random vector. And then, I haven't finished.
Why is H not empty?
Yes, good point. Yes, this would be a trivial, yeah. Yeah, excellent, yeah. Excellent, yeah. Good. 5, output, I haven't stated any theorem about the algorithm. Output, your hypothesis h of x to be sine of w dot x. Okay? And the theorem, or lemma, let's say, is that by careful choice of p and n, just the sizes, this is a weak learner. Okay, is the algorithm clear? I'll do a simulation now. Okay. Adam is puzzled. Good. I think I have 5 more minutes. Great. Right. So we have this universe. We got some red points. This is P. And then we can consider the planes, the normals, that have all of these on one side. So there would be, I know. Now I'm going to draw the opposite side just so I don't crowd this side. So, I could make this like that. This is a normal. Maybe there's a positive point right there, so it's barely touching. And then for this, maybe there's a right? Or let's take it more fun. Okay? So this is all, these are all good, which correctly classify the positives. So far, Isha has no objection, right? There are planes that correctly classify all the positives. Great. Now the trouble is that I'm also picking some negatives. And the negatives can come from anywhere here. And when the negatives comes, I want the negative to be on the same side. So of course, if I get a negative here and a negative here, then this set will become empty. Okay. So what should we do? So what we're going to do is, first let's focus on the positive part for a second, just so that I don't, instead of just stating it. So for the purpose of the positives, just by VC dimension, right? Let me consider just H plus, which is only the planes that have a much lower burden. All they have to do is correctly classify the positives. So that w dot x is greater than 0 for x in positives. Okay? This is some set. This exists because by the thing. And by VC dimension, for any w in H plus, we're going to have the property that the probability that if I pick a new point and ask, what is the chance that I get a negative even though the, which way do I want? Yes, even though the actual label is 1, right? So I get a few of them wrong. Because I didn't see everything, I only saw a sample. Well, that's going to be bounded based on VC dimension. It's going to be something like 100 dimension, which is the log of your sample size divided by your sample size. Okay? Instead of writing in terms of epsilon, I'm just writing the error in terms of the sample size and the dimension. Okay. Now, here's the key. Such planes may not separate any negatives. Right? They're great. They've gotten you, the positives. They're good for the positives, but maybe they don't have any negatives on this side. They're all kind of on this side. That's the problem. So what we're looking for is a good half space. A good half space satisfies the following property in H plus, and that is that the probability over x in D that w dot x is less than 0, given that the label is actually negative, okay, is large. Is at least, let's say, so here it would be only 500, so I want it to be like 500 n log p over p. Only thing to notice is that this is 5 times higher. It's higher. So now if I could find such a w, I'm done. I have a weak learner. Why? Because I take this w, okay? If it outputs negative, I'm going to output label as negative. If it outputs positive, I'll toss a coin. And because it does output negative some fraction of the time, I got a weak learner. And then I continue. It's just a new distribution. Okay. So the game is find a good half space. But as Yishai pointed out, they may not exist. Right? Like, how do we know that they exist? Okay. So here's how we're picking the good half space. We're saying when you pick each negative point, let's ask what fraction of bad half spaces survive. Okay? Now, before that, simple observation, there exists at least one good half space. Why? Because all points were classified by just an intersection of k half spaces. So in particular, there exists a W1 in this set, let's call it W1, such that the probability that W dot x is less than W1 dot x is less than 0, given that f of x is negative, is at least 1 over k. Because every negative point has to be classified as less than 0 by one of the k planes, maybe by more than one, but at least one, and so there's at least 1 over k. Great, so we have at least one good W. Okay, now, but this W may not survive our sample, because we're picking negative samples. So we're going to pick negative samples that only lie on the right side of W1. Okay? N, all x in N are such that, we're just condition are such that W1 dot x is less than 0. Now what's the probability of this? Right? You see? It's only 1 over k to the n. Our success probability is only this much, because all of them have to fall here. Each of the, so the success probability is at least this much. Okay, so I can't make n too big, but I have some room here. Great. And if I get this happens with this probability, I can repeat this so many times and I'll be done. Okay, great. So now the last step is, what is the probability that a bad half space survives? I claim it is at most, we have this 500 n, so it's at most, bad just means this doesn't hold. It's this times k, because we don't know which of them assigned made it bad, one of them, so it's at most this. Now let's ask what's the fraction of the volume of bad spaces in expectation. So the expected volume of bad W is at most this to the power of n times the volume of the ball, upper one. Meanwhile, what's the volume of good half spaces? Once I make this comparable to good, I'm in great shape. I pick a random one, it's going to be. What's the volume of good half spaces? Well, we know this one is good, but not only this, it has a margin. So if there's a little ball around it, that's good. So the volume of good half spaces is rho over 1 plus rho times to the n times volume of B. Why? Because W1 belongs to this set of things, but also W1 plus a little ball belongs to a scaled version of this set. I have to scale it back to make it a unit vector, otherwise. Okay, so I need this inequality to hold, and then my complexity is I've got to run it k to the n times, because the probability of success is only 1 over k to the n, and each time it's the total number of samples I'm doing plus polynomial. And number of samples is p plus n. P is going to be much bigger than n. And now I'm just going to tell you what the parameters we use are. We're going to set p to be some polynomial, you'll see, times 2 to the root n log 1 over rho log k, and n to be just root n log 1 over rho divided by log k. And now you can check that when you do that, these will have the same complexity here, and the overall complexity will be the claimed theorem complexity of this product here, and moreover, this condition is going to be satisfied. The p is just so large, but it's 2 to the root n, and this is only root n, so 2 to the root n times root n, 2 to the n, so it's going to become smaller than this. Okay? And I guess the main lesson here is that for every negative examples, you better have a large number of positive examples. But that's it. That's the whole thing I was going to say. Thank you.
let's see, so, just kind of, okay, so, two questions, actually. So I guess it's interesting here that for normally, like for strong learning, you would need, order n, little n, of positives, order n negatives, and then, and that's what the VC dimension would tell you and so forth. And this is saying, if you want weak learning, so it's enough to get root n points. It's not enough for strong learning, but it's enough to have a reasonable shot for weak learning.
Yes, weak learning with very small probability of success.
Yeah, but
Right.
enough.
Exactly.
Okay, good, good.
When we were thinking about it, the bar was polynomial time. Now, sub-exponential is okay.
So let me ask my second question. So one thing, I think it was in the paper that Ron and I had. So if you just think of k equals 2,
Yeah.
so there's this peculiar thing where if instead of the intersection of two half spaces, you wanted to learn the XOR, so that top region, which is empty in your picture.
Yes.
If that was, actually,
Positive.
that case is easy. If
Yes.
that region is empty, it's easy, because you can pretend it's positive.
Yes.
If that region was positive, the whole thing is easier, because it's now a product of two things, and you can learn it with this.
Yeah.
But just as a product of two things, you multiply it out. But that trick didn't seem to work at all for the and I don't, do you know if, is something like that just not possible? So all these lower bounds kind of require k to be large to kick in. For k equals 2, is it like,
No, for k, there could be a packed learning polynomial time algorithm for k equal to 2.
that just
We have
uses
no-
some, larger, yeah.
Yeah.
That
Some other
particular
concept.
trick just
It can't use a polynomial threshold function, we know
I
that.
guess that-
It has to be
that-
degree n, so it has to do something more than that. That's Scherstoff's bound, I didn't put it up. But it could be some combination of these
That's
things, yeah.
something else, that's still.
So it's a great open problem. We don't know how to do k equal to 2, maybe polynomial times possible. Doing this with random classification noise would be nice. We don't know how to do that. This is not an SQ algorithm, not yet anyway. And of course, better complexity is the main question.
So, quick question, you assume a two-button model, but if you have just random samples with
But you get the label, right? So you just wait till you get enough.
You throw away negative.
Yeah, just yeah, exactly. You keep on, yeah. Yes.
So sometimes running those lower bounds are on running time or also on the sample complexity?
So running time. So SQ algorithm is on the SQ number of queries, and then the crypto lower bounds are on time.
So it's possible, okay, depending on what you believe that
Yeah.
samples can.
No, but the reduction is just reduction to parity with noise. So basically, if you take root n planes, you can write them as intersection of degree 2 polynomial threshold functions. That's where the root n becomes n, and then the root 2 to the n is kind of the lower bound that we know, or that we conjecture.
Or is it having those polynomial numbers? Your time is not polynomial, it's absolutely not fully accurate.